Welcome back. This is Design the Engineering Process, a channel where we give a walkthrough on process engineering operations and design. Let's dive in. For today's content, we will be looking at the first equipment on our model palette, which is the heat exchanger. Before we start, as always, I would advise the new viewers to make sure they watch our previous content to avoid getting lost during today's content, as today's content is a bit mind twisting, but hopefully you will get the hang of it. So, what exactly is a heat exchanger? Let's use this analogy to explain what exactly is a heat exchanger. This is Mary starving inside the kitchen. Mary heads over to the freezer to get food. Fortunately for Mary, Mary finds a bowl of soup. Unfortunately for Mary, the bowl is frozen. Now Mary still has a problem. And then Basaka steps into the kitchen to save the day. Mary explains her situation to Basaka, and Basaka says, "I have a brilliant idea." Basaka gets a bowl of hot water. Mary looks at Basaka cluelessly. Basaka demonstrates the process of heat exchanging. Unfortunately for Basaka, he ends up deviating from heat exchanging to mixing. And Mary still has a problem. Double problem, actually. A heat exchanger is a device designed to transfer thermal energy between two or more fluids, liquid, gases, or both, at different temperatures without mixing them. Types of heat exchangers include shell and tube heat exchanger, which we commonly use on ASPEN HYSYS, plate heat exchanger, air-cooled heat exchanger, double pipe heat exchanger, spiral heat exchanger, and there are a lot of them. This is just me narrowing them down for this content. So, why use a heat exchanger when you have heaters and coolers? Energy efficiency. Heat exchangers allow direct transfer of thermal energy from a hot stream to a cold stream, minimizing the need for external heating or cooling using coolers or heaters. Naturally, if we would want to carry out heating operations and cooling operations, we require a lot of energy for the independent operations of heating and cooling separately. But with a heat exchanger, you could simultaneously do them at a lower energy consumption rate. So the heat exchanger is basically like an optimization of the coolers and heaters operation, lower operation cost. By recycling heat exchangers decrease the consumption of energy, fuel, or electricity needed to heat and cool fluids separately, thereby reducing utility operation cost. The lower operation cost is still tied to the energy efficiency. They go hand in hand. The lesser your energy consumption, the lower your operation cost. Alright, so let's reflect back at the scenario we had between Mary and Basaka from the kitchen. Putting it in a diagram, we could say that Basaka's hot water was reading at a temperature of about 90 Celsius. Mary's frozen bowl of soup was reading a temperature of about 0 Celsius. So, if the bowl represents the heat exchanger, let's just hypothetically imagine that Basaka's water was passing through the bowl while Mary was dropping her frozen bowl of soup inside. With this, we believe that there is no mixing between the two fluids. Of course, we assume that Basaka did not allow Mary's soup to sink inside the bowl. But going by what we have from the diagram and the rule of heat exchanging, the two fluids do not mix together. It's just a thing of thermal energy transfer between one fluid to another through a medium separating them. The two fluids do not mix. With this interaction, we believe that Mary having a temperature of 0 Celsius and Basaka having a temperature of 90 Celsius after thermal energy transfer between their two fluids, Mary ends up having an end temperature, an outlet temperature of 70. So we believe our soup comes out hot at a temperature of 70 Celsius, and Basaka's hot water comes out at an outlet temperature of 20 Celsius, coming out cold, and Mary's cold soup coming out hot. With this, if we do a little calculation, we could see that our change in temperature is about 70 Celsius. So we transferred 70 Celsius from Basaka's hot water to Mary's cold soup. And now Basaka has a temperature of 20 Celsius for his water, and Mary has a temperature of 70 Celsius for her soup. So let's say we go back to the kitchen and change the whole scenario between Basaka and Mary. Let's say this time around Mary has 2 bowls of frozen soup, and Basaka still has his boiling water, his hot water, a single bowl of hot water at a temperature of 90 Celsius, and Mary still has a frozen bowl of soup to be 0 Celsius. But remember, this time around Mary has 2 bowls of frozen soup. The 2 bowls go inside the heat exchanger. Basaka's hot water goes into the heat exchanger, and this time around, if you do the little calculation, you could see that our change in temperature has a slight variation. The change in temperature for Mary's scenario is it's 35 Celsius, because for you to calculate the change in temperature for a substance, it's the final temperature minus the initial temperature. Going by that, we have our final temperature for Mary's scenario to be 35 Celsius and her initial temperature to be 0 Celsius. So if we do that mathematically, we have 35 minus 0, which equals 35. Unlike the first scenario where we're having 70 as our 70 Celsius as our change in temperature for Mary's scenario, this time around it's 35 because we're having 2 bowls. And there's a reason for this. There are 2 factors which affect the transfer of thermal energy between 2 fluids in a heat exchanger. The whole operation of a heat exchanger is based around 3 things to maximize and to increase and decrease the transfer of thermal energy between 2 fluids, streams, however you wish to call it. Well, before we leave and discuss those other things, let's check the change in temperature for Basaka's scenario. The inlet temperature of Basaka's hot water was 90 Celsius, and it came out at a temperature of negative 20 Celsius this time around. So to calculate our change in temperature, it's the final temperature minus the initial temperature. Our final temperature for Basaka's case is negative 20 Celsius minus his initial temperature, which is 90 Celsius, which gives us a negative 110 Celsius. Remember we said that there are factors which affect thermal energy transfer beyond change in temperature. Let's have a look at what exactly are these factors. But before we do that, we need to understand where they are derived from, where they do stem from. From the first law of thermodynamics, which states that the change in internal energy of a system is equal to the heat added to the system minus the work done by the system. Mathematically speaking, we have change in U equals to Q minus W, where U stands for internal energy, Q stands for heat, and W stands for work. Working with the assumption that the work done of our heat exchanger is 0, we write our equation to be change in internal energy equals Q minus 0, and we get the equation called sensible heat transfer equation. This brings about the relationship between heat and mass, which equates to change in internal energy equals mc change in theta. And this m stands for the mass flow rate. I need you to take notes of every single thing we are looking at right now. Mass flow rate, C stands for specific heat capacity, the T stands for change in temperature, which we already discussed earlier, which is nothing more than your final temperature minus your initial temperature. Therefore, we equate back the heat to be, remember that we said our du equals Q, and we have a value for our du to be mc change in theta. So our Q, which is our heat stance, is equal to mc change in theta, mass flow rate times specific heat capacity times change in temperature. So these three parameters significantly affect our change in heat transfer, thermal energy, heat transfer in a heat exchanging process. Less English, less math. Let's just sum up every single thing we've been saying since. Increase in mass flow rate leads to increase in heat transfer and the vice versa. We're going to discuss that in a jiffy. Increase in specific heat capacity leads to increase in heat transfer and the vice versa. That's also. Increase in change in temperature leads to increase in heat transfer and the vice versa. We already discussed that earlier. Due to the direct proportionality between the change in temperature and the heat transfer, the higher your change in temperature, the more it increases your heat energy transfer. As for the mass flow rate, let's look at it from this perspective. If I have a bottle of cold water and 2 bottles of hot water and I mix that, I'm expected to have a water somewhere, the temperature of my water should be somewhere around warm to hot. This is because I have more. The amount of my hot water is more. So this is exactly what the mass flow rate is talking about. The quantity significantly affects your heat transfer, the rate of your heat transfer. So let's try the scenario the other way around. If I have 2 bottles of cold water and a single bottle of hot water and I mix them up, I'm expected to have my water temperature to be somewhere around warm and below warm. You could say cold or lukewarm. So the change in temperature, like we said earlier, is not the only factor that plays a significant role in our heat transfer. The mass flow rate also plays a very significant role. So instead of you having a very, very high temperature for your hot stream, just to be able to transfer enough energy to the cold stream, enough heat energy to the cold stream, you might just want to temper a little bit with your mass flow rate to make things balance up. It goes a very long way too, because it's also directly proportional to your heat transfer. As for the specific heat capacity, this is a physical property of a substance that describes the amount of heat energy required to raise the temperature of 1 unit mass of a substance by 1 degree Celsius. Now, this is something a bit complicated, and in most cases for thermodynamics, the fluids do have a specific heat capacity always. It doesn't change that much. It's something mostly constant. But majorly, the two major things we should look after in the heat exchanging process is our change in temperature and the mass flow rate to significantly affect our heat energy transfer from one fluid to another, from one stream to another. So let's practicalize what we just discussed about these 3 parameters affecting the heat transfer. So this third scenario covers Mary having 2 bowls, that's same 2 bowls of frozen soup, but this time around Basaka has 2 bowls of hot water also. Let's see if that works. What we just did right now, we did not temper with the specific heat capacity, we did not temper with the change in temperature. It's still the same scenario, 0s and 90. The lower limits, Mary having the lower temperature of 0 Celsius for all her 2 bowls, and Basaka having the higher temperature limit of 90 Celsius for his 2 hot water bowls. But we tempered with the mass flow rates. That's our M. This time around, Basaka is having more quantity of hot water than the first scenario and the second scenario. So after the heat exchanging process, our change in temperature adds up to be 90 Celsius. Yes, 90 Celsius for Basaka's case, and for Mary's case it's also 90 Celsius. So Basaka lost 90 Celsius to get his temperature, his hot water's temperature, to a low temperature of 0 Celsius this time, coming out the outlet of the heat exchanger, the outlet of the bowl for Basaka's water is now cold, having a temperature of 0 Celsius, and Mary's cold frozen bowl of soup comes out to be hot at a temperature of 90 Celsius. The two of them were able to attain 90 for the both of them. But for in our second scenario, due to Basaka having less amount of hot water compared to Mary's two frozen bowls, he didn't have enough energy to transfer to make Mary's two bowls of frozen soup hit that temperature of 90 Celsius. They were only able to get themselves to a temperature of 35 Celsius each. So with this, we confirm that the parameter of our mass flow rate significantly affects our heat transfer, the rate of our heat transfer. Remember, it's three things: mass flow rate, specific heat capacity, change in temperature, and majorly in heat exchanging, we deal with these two parameters: the mass flow rate and the change in temperature. While operating the heat exchanger, with time we get to fall across a certain phenomenon called temperature crossing. What exactly is temperature crossing? Temperature crossing is a situation where the temperature of the cold stream outlet in a heat exchanger comes out as hot as or hotter than the temperature of the hot stream outlet. Basically, the cold stream outlet comes out with a temperature equal or greater than the temperature of the hot stream outlet. This can cause failure in shell and tube heat exchanger operations, and it is not desired. In ASPEN HYSYS, we majorly use shell and tube heat exchangers to carry out operations. So with that, temperature crossing is not desired. Temperature crossing in shell and tube heat exchangers is perceived as an error. So you will always need to work on that. Some special heat exchangers can operate with temperature crossing, but they cost more resources. Heat exchangers such as plate heat exchanger. What exactly does the temperature crossing and no temperature crossing look like? On the left-hand side of our screen, we have the temperature crossing scenario, and on the right-hand side, we have no temperature crossing scenario. Let's look at the left-hand side of our screen, the temperature crossing scenario. As we can see, we have an inlet temperature, a hot inlet temperature of 100 Celsius, and it comes out of the heat exchanger at a cold temperature of 20 Celsius. And we have a cold inlet stream having a temperature of 20 Celsius coming out as a hot outlet stream of 100 Celsius. With this, we do our change in temperature balancing for the hot inlet coming out as a cold outlet. And we have a negative 80 Celsius as our change in temperature. So we need to take note that in thermodynamics, the negative always stands for losses and the positive stands for gains. So with our case, dropping from a temperature of 100 Celsius to 20 Celsius, we have a negative 80 as our temperature, change in temperature. Then for the inlet cold coming out as a hot outlet, we have a gain of a positive 80 as our change in temperature, a positive 80. So with this, we just had temperature crossing. Remember, it says that the cold temperature comes at the cold outlet temperature comes at a temperature equal to or greater than the temperature of the hot outlet. So our hot outlet is the 100 Celsius coming out as a cold temperature at a cold temperature of 20 Celsius, and the cold inlet comes out at a outlet temperature of 100 Celsius. With that, it comes out hotter than the hot stream which goes into the heat exchanger. With that, we have temperature crossing, and that is not desired in the shell and tube heat exchanger. It sounds a bit confusing, but when we get to model, you would understand more. For the low temperature crossing scenario, we have an inlet temperature for a hot stream to be 100 Celsius, and it comes out at a temperature of 65 Celsius. It's colder. It lost a temperature of, has a change in temperature of negative 35 Celsius. And then the cold inlet temperature comes out at an outlet temperature of 55 Celsius. It has again a change in temperature of positive 35 Celsius. With this, if you compare the stream, the inlet hot stream comes out at an outlet temperature of 65, still greater, hotter than the cold inlet stream coming out at the temperature, a hotter temperature of 55 Celsius. If you compare them, 65 is still greater than 55. With that, we do not have a temperature crossing, and we have successfully operated our shell and tube heat exchanger. We're back to the modeling environment and we're ready to operate our heat exchanger. But before that, remember, before you get to the simulation environment for every single process, you need to do two paramount things. Select your component list and your fluid package. For this operation, I will be using H2O and N-octane as my component list. Two components, H2O and N-octane. And as always, our fluid package is Penn Robinson. So let's drop two streams. The reason for two streams is that for a heat exchanging operation, you need two or more streams to interact. Having one of the stream to be at a high temperature, hot temperature, and the other one to be at a lower temperature, colder temperature. With this, you create a scenario where there is thermal energy transfer between the two streams or more streams. It could actually be more than two streams, but for this content, we will be using two streams. Exchanging thermal energy between two streams. We're expecting the hot stream to transfer its heat, its thermal energy to the cold stream. The cold stream gains thermal energy, gains more heat, rises, the temperature rises, and as for the hot stream, initial hot stream, it loses its heat and becomes colder. And that's exactly what we're doing. But remember, in a shell and tube heat exchanger, which we mostly deal with in ASPEN HYSYS, you need to bear in mind that there are phenomena such as temperature cross, which is an error because it's an error in operation, and you need to avoid that kind of error. So we will work with that. And temperature crossing is nothing more than the colder stream coming out hotter, the initial cold stream coming out hotter than the initial hot stream. As hot as or hotter than the hot stream. So let's practicalize every single thing we've been saying. We have two streams here. Let's name this octane. This stream stands as Basaka's hot bowl. We could use this analogy to link what we've been discussing and what we're about to practicalize. This octane represents Basaka's hot bowl. Remember, Basaka's hot bowl was water. What was inside was water. So let's give a vapor fraction of 0. The temperature was 90 Celsius. Let's give it a mass flow rate. Let's allow ASPEN HYSYS to give us the pressure. Today we are working with mass flow also, 1000 kilogram per hour. That's our mass flow composition. Remember, it's a stream of octane, so 100% octane. But before that, we change our compositional basis to mass fractions. So octane, 100%, 1 rather, which represents 100%. And with that, we've successfully created our octane stream, and it's having a pressure of 0.3354 bar. That's quite low. That's quite low. So let's do something to work on that pressure. It's quite low. Let's make it more realistic. Let's give the stream the pressure, and ASPEN HYSYS gives us the vapor fraction. Let's say it's at a pressure of 3 bar. Yeah, that's better. You can see ASPEN HYSYS automatically gave us the vapor fraction to be 0. So we're good with the octane stream. Now let's create this stream to be water stream. But before that, we could just do this customization. Head to your flow sheet / modify. Click on rotate. This rotates the stream to your direction, preferable direction. So let's make this back to the home environment. Okay. So let's call this stream H2O. Let's remember H2O, Mary's frozen bowl. Even though it was solid, but we cannot represent solids in ASPEN HYSYS. So let's just give it a vapor fraction of 0, signifying it's actually liquid. It's a liquid at a very cold temperature. Let's give it a vapor fraction of 0. Then let's give it a temperature, a cold temperature of, let's say, 0 Celsius. That's what Mary was having, 0. Let's allow ASPEN HYSYS to give us the pressure. Let's also give it a mass flow of 1000 kilogram per hour. Composition, mass fractions, H2O 100%. With that, we've successfully created our stream. Wow, and it's also having a very, very low pressure of 0.00059 bar. So let's work on that. Let's just allow ASPEN HYSYS to give us the vapor fraction. Let's give it a pressure of 1 bar. Good, that's perfect. And with that, we have our 2 streams successfully created. Now, 90 Celsius, this is the hot stream. 0 Celsius, this is the cold stream. We will be using our heat exchanger to exchange the heat, transfer the heat between these 2 equipments. These 2 streams, rather. Okay. So, as you can see, the heat exchanger looks like the heater and the cooler. The only difference is that the heat exchanger, the 2D icon for the heat exchanger, doesn't have an arrow going up or down on it. It's just a round icon, 2D icon, with a little crack, I would say, in the middle. But for the heater, it has an arrow going down, and for the cooler, it has an arrow going up. So this is the heat exchanger. Double clicking. We're currently inside the heat exchanger environment. So, unlike any equipment you've dealt with before, the heat exchanger has 2 inlets and 2 outlets. The tube side inlets, the shell side inlets. That's 2 outlets. The tube side outlets, the shell side outlets. That's 2 outlets. Now, remember what we call this equipment: shell and tube heat exchanger, or in some scenarios, it's called tube and shell heat exchanger. Now, let's explain this to a relatable fashion. Imagine you having a bottle of Coke and you place a straw inside. The straw is the tube submerged inside the Coke, and the bottle of the Coke is the shell. This is basically what the heat exchanger, shell and tube heat exchanger looks like. The tube is submerged inside the shell. Now, the reason for this equipment being like this is due to some factors such as optimization of thermal energy transfer to make it more efficient, and safety factors. Let's talk about the safety factors first of all. Imagine a scenario where you're dealing with a hazardous fluid and a non-hazardous fluid to the environment. In an event where you place your hazardous fluid inside the shell, which is closer to the environment, and you place the non-hazardous fluid inside the tube, in an event of leakage from heat exchanger on the shell, the part of the shell, the hazardous fluid easily leaks to the environment, causing a disaster, a safety factor disaster, a safety factor disaster. And this is not desired when carrying out operations. So instead, you put the more hazardous fluid inside the tube, and you place the the less hazardous one inside the shell. By this, when you have a leak from your shell, the non-hazardous fluid is the one that leaks out, which isn't much of a problem, can easily be handled. And if by any chance the tube is leaking and the shell is alright, the hazardous fluid leaks out of the tube into an extra protection layer, which is the shell, without reaching the environment. This is one of the factors. The second factor is the thermal energy transfer efficiency. In a situation where you do want to achieve as much heat transfer as possible, you place your fluid that you need to gain the heat inside the tube, because the tube is submerged inside the shell. It has more room for heat energy transfer. It's able to absorb more heat from the shell inside the tube. The tube travels along the heat exchanger, going round, spending more time inside the shell. With that, it has more time to absorb the heat it needs as best as possible. These are the two factors. But in ASPEN HYSYS, it doesn't really matter which goes into which. It doesn't affect your process. This is a real life scenario application, only a rule of thumb from the real life operations. So in ASPEN HYSYS, we could put whichever we wish wherever. Let's just place the octane inside the tube and the H2O inside the shell. Those are our inlets. We have them on ground, so we place them. As for the outlets, we do not, so we have to label them. Octane out and H2O out. Perfect. And like our heaters and our coolers, we do need to specify change in pressure. Now, bear in mind that in real life applications, it's not the same in ASPEN HYSYS modeling and simulation. Or real life applications, in heat exchangers, we typically have a pressure drop of about 0.1 to 1 bar. Pressure drop in real life applications, but for ASPEN HYSYS, we could work with anything a bit more than that. So just keep in mind to be able to relate to the real life scenarios, but it doesn't affect our operations that much. So you can see we have 4 streams, the 4 streams connected to our heat exchanger. The tube in, which is our octane, the tube out, which is our octane out, the shell in, which is our H2, the shell out, which is our H2 out. And you can see that our outlets do not have any value, any attributes attached to them. They're empty. So remember, it's asking us for the pressure, change in pressure. So let's say our change in pressure is just 1 bar. 1 bar. And you need to know, before you carry out an operation in heat exchanger, you need to know which stream is giving out energy and which stream is receiving energy. Certainly the hotter stream gives out heat energy, and the colder stream receives heat energy. So now let's impute a pressure, change in pressure first of all. Because octane is giving out heat, so let's say it loses 1 bar. 1 bar, change in pressure is 1 bar, so change between 3 bar and 1 bar is equal to 2 bar. 3 minus 1 bar, that's 2 bar. And let's say H2O is gaining 1 bar. That makes it 2 bar. 1 plus 1, 2. That's perfect. So we still have a message saying underspecified. Now let's specify the outlet temperature of any of the two, the octane out or the H2 out. But bear in mind that we cannot have temperature crossing a situation where the outlet temperature of the colder stream comes out hotter than the outlet temperature of the hotter stream. Temperature crossing, because this is a shell and tube heat exchanger, that's an error. It causes an error in our operation that is not desired. So let's say the outlet temperature of our octane after losing heat is about 60 Celsius. And ASPEN HYSYS automatically finds the temperature of the 4th variable, our outlet, H2 outlet, to be 16.4 Celsius. With that, thermal energy transferred has occurred, heat exchanging has occurred. Octane lost 30 Celsius to give H2O 16.4 Celsius. Now, not like the scenarios we had back for Basaka and Mary's hot bowl of water and frozen soup, where it loses 70 Celsius from Basaka's 90 Celsius and gives Mary 70 Celsius. it doesn't always have to be like that. It's not equal because there are factors affecting this heat transfer, like we said, the mass flow rate, the specific heat capacity, and changing temperature. So things that you do to make it more optimal is increasing your specific heat capacity, which isn't something easy to do in ASPEN HYSYS. Mostly what we do is we increase our change in temperature and change in mass flow rate. The higher your mass flow rate or higher your change in temperature, the more heat transfer you can achieve. And what we worked on right now was the change in temperature. The change in temperature between the octane stream is 30 Celsius, negative 30. It lost 30 Celsius to be able to give H2 a positive 16.47 Celsius. So now let's try and squeeze out more heat. By that, let's increase our change in temperature. Let's say it goes from 90 to 60. From 90 to 60, it's now currently 90 to 40. By that, we were able to squeeze out 60 Celsius, negative 60. It lost negative 60. And let's see what it's going to give the H2O outlet. Alright, so when having a change in temperature of negative 60, we're having a temperature of positive 26.86 for our H2O. That's the new temperature. But remember, temperature crossing, we do not still have a temperature cross. This temperature for the cold stream is still lesser than the temperature of the hot stream outlets. This is 40 and this is 26. 40 is greater than 26. With that, we do not have a temperature cross. But then let's do something. Let's make our change in temperature for our octane streams. Let's make it this time around 90 to 30. By that, we are having a change in pressure of about 60 Celsius. Let's make it 30. And with that, we have an outlet temperature of 31.88. But I need you to take note of something. Remember, temperature crossing. 31.88 Celsius. It's coming out hotter, slightly hotter than the outlet of the hot stream, which is octane out. But the difference between 30 and 31.18 is 1.88 Celsius. And ASPEN HYSYS is not able to recognize that as something severe for a temperature cross. So it's able to overlook that error and allow us to operate. But it's not desirable inside your heat exchanger, shell and tube heat exchanger. So let's say we increase this change in pressure for our octane and make it 70 to 20 now, having a negative 70 loss of heat. Let's say it's 20 right now, 20 Celsius. Voila. We have a temperature for our hot stream outlet to be 20 and an outlet for our cold stream to be 36.78 Celsius. With this, we have a temperature cross. FT correction factor is low. It's basically talking about the temperature crossing. ASPEN HYSYS is able to take note of that to verify that that is a temperature cross and is not desirable. And with this, we have not successfully solved our heat exchanger. So let's say we make it, instead of a negative 70 change in temperature, let's say we're having a negative 65, having 25 Celsius. With that, we're still having temperature cross. Let's say we have a negative, instead of negative 65, we're having a negative 61. Let's say this is 29. As you can see, 29 is not too far from 32.37. This is also a temperature crossing, while ASPEN HYSYS is not able to take note of that. Let's make it 28 Celsius. And ASPEN HYSYS is able to take note of that as a temperature cross, which is not desired. So this is basically the heat exchanger doing its operation of transferring heat from a hot stream to a cold stream. The hot stream loses its heat and the cold stream gains that heat lost. And factors which affect this majorly in ASPEN HYSYS is the change in temperature and mass flow rates. The specific heat capacity also does that, but it's something a bit more complex for the scenarios to bring in. But hopefully you might see that in the future. So let's just correct this. Let's make this 50 Celsius. Yeah, it's perfect. Let's see if we can squeeze out more energy. Let's say this is 35. Yeah, we're able to do that. So we have a change in temperature for the octane, the hot stream, to be that's about 30. Is that 65? No, that's about 45. Is it? Yeah, actually, no, 55. Yeah, so that's perfect. Change in temperature for outlet stream, hot inlet and hot outlet stream, octane inlet, octane out, to be 55 Celsius, negative 55 Celsius. It loses negative 55. It loses a heat of 55 Celsius, and the H2 gains a temperature of positive 29.39. That's again 29.39 Celsius. So with this, we believe that we have squeezed out as much, or rather, let's try and do that. Let's squeeze before we get a temperature cross. This is 31, and with this 31, we have a temperature cross, which is not desired. ASPEN HYSYS cannot take note of that because the range is very minimal. It's very small for ASPEN HYSYS to take note of, but going by the rule where the cold stream cannot come out hotter than the hot stream, this does not work for us. It's also a temperature cross. So let's say 32. Yeah, this is perfect. 32 is still hotter than 30.89. With this, we believe that we have squeezed out as much energy as we can. We have reached the best temperature we can before heating a temperature cross. But then remember, we said that things that affect this heat transfer is mass flow rate and change in temperature for ASPEN HYSYS. So we just worked with the change in temperature, and we believe that we have achieved the best we can before heating that temperature cross error. So now let's try working with the mass flow rate factor, which is our M in the equation, sensible heat equation. Remember what we said about Mary having 2 bowls of frozen soup and Basaka having 2 bowls of hot water? It makes the thermal energy transfer more efficient. Remember from our sensible heat equation, the 3 parameters affecting our heat, our thermal energy transfers, the MC, change in theta, change in temperature, and that's what we just did inside our heat exchanger. We optimized to get the highest value we could get for our change in temperature. As for the specific heat capacity, that's something a little bit too complex to deal with. So we will be also dealing with the mass flow rate to see what we can get from it. So if this time around Basaka is having a flow rate for each bowl, he's having a flow rate of 1,000 kilogram per hour. That's like the amount of hot water inside the bowl. If we're talking about 2 bowls, Basaka would be having 2,000 in total, 2,000 kilogram per hour. So we will be creating 2 streams to be connected to the heat exchanger, but you cannot connect 2 streams to the inlet of a heat exchanger. So we will have to be using a mixer to mix 2 streams into a single stream and then connect them. That was our previous content. In case you haven't seen that, the link will also be in the description. But then using a mixer takes time and space in our modern environment, so we could just manually do it and just make this 2,000 kilogram per hour instead, and that solves the problem. All the same with mixing it, and with that we've altered our mass flow rate. We have increased it, and we expect that our we expect that the rate of heat transfer, thermal energy transfer increases, and it just did. Earlier we were having 20 something for our outlet temperature for our H2, but after doubling our mass flow rate, increasing our mass flow rate, the rate of heat transfer increased significantly. It doubled to 48.86. So this is how the mass flow rate affects the heat transfer. It's just like having a bowl. It's just like having a bottle of hot water and a single bottle of hot water and 2 bottles of cold water. The heating wouldn't be as efficient as having 3 bottles of hot water and 2 bottles of hot water. the heating would be more efficient in the 3 bottles of hot water against 2 bottles of cold water. So this is exactly what we did. So let's try and squeeze out the best we can from the energy to see what we can get. But remember, this is a shell and tube heat exchanger, and we are currently having temperature cross, but it's very minimal. So ASPEN HYSYS is not able to trace that. So let's just fix that up. Let's say we have 45 instead. Yeah. With 45, we're still having a temperature cross. Let's say 49. Alright, no temperature crossing at 49. Let's make it 48. No temperature crossing. Make it 47. No temperature crossing. Let's say 46. And with 46, we have temperature crossing. So let's say 47. Let's say we have 47. And with this, we have successfully operated our heat exchanger using the mass flow rate factor to improve our heat transfer, the rate of our heat transfer, thermal energy transfer. So remember, changing temperature and mass flow rate are majorly the two parameters which affect our heat transfer, our energy transfer from our sensible heat equation when we apply this in ASPEN HYSYS. The third factor is the specific heat capacity, but we're not using that. So with this, we have covered the second parameter from the equation. This is what it looks like in the modeling and simulated environment. You can see the hot inlet temperature to be 93 bar. It comes out at 44.82 bar. That's the tube out, tube in. H2, that's the shell in, 0 Celsius 1 bar. Shell out, 2 bar, 48.6 Celsius. Exactly what we saw inside the worksheet for the heat exchanger. The tube goes in, the shell, H2O shell goes in, comes out, shell out. Tube in, tube out. And that's what it looks like after you successfully operate a heat exchanger. So imagine you try and optimize this process. We've just tried to optimize it maximizing the thermal energy transfer through maximizing the change in temperature, maximizing the flow rate, even though we could actually maximize more than the 2,000 kilogram per hour mass flow rate. We could maximize it, make it 3,000, 4,000, as much as we wish. But what if we do not want to maximize the amount because it could cause some kind of problem in our process engineering operations? What could we do? Imagine having 2 heaters heating a specific stream. One heater, the first heater, heats it from 0 Celsius to 100 Celsius, and the second heater heats it from 100 Celsius to 200 Celsius. That would be amazing. The reason for using 2 heaters is maybe you do not want to strain the first heater to heat it from 0 to 20, because that would require a lot of energy, generate a lot of heat, consume a lot of energy, and you use 2 heaters to reduce the workload. So is that possible in ASPEN HYSYS to have 2 heat exchangers doing this operation of this specific operation of having 2 heaters to reduce the workload? Could you use 2 heaters, 2 heat exchangers to maximize the thermal energy transfer to reduce the workload on one heat exchanger and maximize the heat energy transfer? Well, yes, it's actually possible, and that process is called a heat exchanger train. What exactly is a heat exchanger train, and how does it look? In process engineering, the utilization of heaters and coolers consume more energy and, of course, more resources. Therefore, heat exchangers are used to optimize these processes, heating and cooling. You could think of the heat exchangers as a 2-in-1 package, certainly, because it's it's a cooler and a heater together in one equipment. Imagine if we did not have heat exchangers, we'd be having coolers and heaters. We'd be buying coolers differently and heaters differently, and they cost more. They consume more energy, and thereby the utility cost rises a lot. But with the heat exchanger, you minimize the cost, the energy consumption, and so on. But then what happens when higher and lower temperatures are required for a certain operation? What we just discussed earlier about the load. If we require higher and lower temperatures for an operation, we would be using a heater to heat at a very high temperature, but that would consume more energy, more load, which could be a safety problem. With this, you have two heaters to heat the specific temperature from 0 to 100, and the second heater heats from 100 to 200 for you, but that costs more. It consumes more energy, costs more. Now you're having two heaters because you want to abide by the rule of the safety, to abide by the safety factors for an operation. But why not just use a heat exchanger which has a heater and a cooler and costs less for operation? Why not just use that? So this is where the heat exchanger train comes in. Instead of having two heaters, three heaters, you could just have a heat exchanger, but this time around having two heat exchangers, three heat exchangers. A heat exchanger train, basically a combination of two or more heat exchangers interconnected to achieve heat transfer between fluids. And this is what a heat exchanger train looks like. So let's go back to the kitchen scenario and make a little bit of an alteration to the process. So let's say this time around Mary's having 3 bowls of frozen soup. Basaka's having 1 bowl of hot water, and the temperature of Basaka's hot water is 100 Celsius currently, and Mary is having 3 bowls of frozen soup. The first bowl is having a temperature of 20 Celsius, the second bowl is having a temperature of 10 Celsius, and the third bowl is having a temperature of 0 Celsius. So if Mary places the first bowl having a temperature of 20 Celsius inside Basaka's hot water, the new temperature for Basaka's hot water is 65 Celsius, and the new temperature for Mary's cold bowl of soup is 55 Celsius. Thereby, Mary's bowl gains heat and becomes hotter, and Basaka's hot water becomes colder. But bear in mind that this is a shell and tube heat exchanger, train. So we need to bear in mind that temperature crossing is not allowed, and this is exactly the reason why the outlet temperature of Mary's cold bowl is still lower than the temperature of Basaka's outlet, hot outlet of Basaka's hot bowl of water. Basaka's hot bowl of water is 65 Celsius. Mary's cold bowl of soup is 55 Celsius. So it goes into the second heat exchanger because this is a heat exchanger train, and now Mary introduces a new bowl of cold soup. It's frozen. Hypothetically, it's frozen, but going by the temperatures, water freezes at a temperature of 0 Celsius and some other fluids. But let's just look at it hypothetically. It's a frozen bowl too, having a temperature of 10 Celsius. It goes into the second heat exchanger, and this time around Basaka's hot water is at the temperature of 65 Celsius. So the thermal energy transfer, the heat exchanger does the stuff of transferring heat between the two fluids, and Basaka's new temperature coming out of the heat exchanger is 45 Celsius, and Mary's new temperature is 30 Celsius, still less than Basaka's hot outlet temperature. So no temperature crossing, and then it goes to a third heat exchanger because this is a heat exchanging train. So the third bowl is having a temperature of 0 Celsius. It's introduced to the heat exchanger, and Basaka's new temperature is 25 degrees Celsius, and Mary's new outlet temperature is 20 Celsius. With that, there is no temperature crossing throughout the heat exchanger train. So what we just did was optimizing the heat exchanging process. Instead of having a single heat exchanger having the strain of load of you maximizing your mass flow rate or maximizing your changing temperature, what we just did, we just spread the load across 3 heat exchangers to optimize the process. Instead of having to use 3 heaters to do the whole process of heating Mary's bowl, or having 3 coolers to do the whole process of heating Basaka's hot bowl of water. We just used a heat exchanger and it simultaneously did the two operations of heating and cooling all through, and everybody walks home happy. So the heat exchanger train is the process of optimizing heat exchanging operations. You can have a train of 2 heat exchangers, 3 heat exchangers, 4, and as much as you desire for your particular process. So this is what it looks like. All right, so what we just need to do is we already have our first heat exchanger perfectly working. So we just drop a second heat exchanger. Let's drop a third heat exchanger to make it 3 heat exchanger, a train of 3 heat exchangers. And with that, let's create 2 extra streams representing Mary's second and third bowl. But Basaka only has 1 bowl of hot boiling water. Yeah, a single bowl reading 90 Celsius. So let's just customize this and this back to the home environment. So let's name this H2O. H2O2. Yeah. And as usual, we're going to do our lazy, convenient thing of defining the stream. Let's use H2O1 to define it. Alright, so let's work on temperature this time around. Should we still work with the same temperature of 0 Celsius? Let's see, what temperature do we have our outlet temperature to be? It's coming out at temperature of 48. Alright, so I think that would still work. So let's also do this definition. H2O. This time around, instead of working at a mass flow rate of 1000 for the third stream, H2O3, let's just erase this. Let's work at a mass flow rate of 3000 kilogram per hour. That's perfect. So let's do our connection. Remember what we witnessed for our heat exchanger. We had Basaka's bowl, only a single bowl from Basaka, entering the heat exchanger throughout, but Mary had 3 bowls. So that's exactly what we're trying to represent. Over here. We have 3 bowls. Mary has 3 frozen bowls and Basaka has 1 hot bowl of water. So to make our heat exchanger train work, we will connect our tube with our octane outlet as the tube inlet, and just name this octane out 2. For the inlet, it's the Mary's second frozen bowl, which is H2O2. We will call it H2O2 out. Alright, and remember, heat exchanger, we need to specify our change in pressure. So let's say this time around we're having 2 points. No, it's losing heat. Remember, Basaka's bowl is losing heat, so let's say it's 1.5 bar. And let's say the second bowl needs a pressure of 5 bar, 0.5 bar, 1.5. That's perfect. So let's say the temperature, the outlet temperature this time around comes out at about 30. Yeah. And with that, we successfully operate our heat exchanger, our second heat exchanger, and we have successfully connected the second heat exchanger to the first one to have a heat exchanger train of 2 heat exchangers. So let's try and optimize this using our change in temperature. Let's say it drops to 20 Celsius instead, and we have a temperature cross. So let's say it's 25 Celsius. We do not have a temperature crossing. Let's say it's 22 Celsius. We have a temperature cross, but ASPEN HYSYS is not able to trace it. So let's say it's 23. We do not have a temperature cross. That's perfect. Just space this out. Pull this up. Pull this away. And it's perfect. So with that, we have successfully operated our second heat exchanger. We have a heat exchanger train of 2 heat exchangers, but we desire 3, a trade having 3 heat exchangers. So let's connect the third one. Remember, the outlet temperature of Basaka's bowl currently is 23 Celsius. It dropped from 44.8 to 23.0 Celsius, 23 Celsius. So connecting the third heat exchanger to our train, we have our outlet 2, and we have the, let's call this octane out 3 for the tube outs, and we have our third bowl on ground, so H2O3, and we call this H2O3 out. Perfect. And we specify the change in pressure. So let's say this is 1 bar, and this is 1.5 bar also. Now on the specified, and we specify our temperature. Let's say it comes out at 5C, and that perfectly works. Remember, this time around we are having the mass flow rate factor. We are not only working with the change in temperature factor to maximize the efficiency of our heat transfer. We are also working with the mass flow rate. The mass flow rate for Basaka's bowl currently is, but Basaka is having a mass flow rate of 2,000 kilogram per hour, and Mary is having 3,000 kilogram per hour for this at third bowl. So it means the quantity of frozen soup is greater than the quantity Basaka is currently having right now. With that, we expect that the heat transfer would be more efficient. And we currently do not have a temperature cross, but let's try and make this 4 instead. And we have a temperature cross. So let's try and make this 4.5. We have a temperature cross. 4.8. Temperature cross. 5. Alright, 5 is perfect. No temperature cross. Alright, so with this, let's just fix this up. With this, we've successfully created a heat exchanger train. Now let's do a heat tracing to see. This goes in, Basaka's bowl goes in at 90 Celsius. Mary's first bowl, 0 Celsius. So Mary's first bowl comes out at a temperature of 48.86 Celsius. It gained 48.86 Celsius from Basaka's hot bowl. Basaka transferred that heat to Mary's first bowl. So Basaka's bowl comes out at a temperature of 48.80 Celsius, losing a temperature of about 45.2 Celsius after the heat exchanging. But remember, this is a heat exchanger train. So it goes into the second heat exchanger. Mary's second bowl, this time around, is coming out at a temperature of 0 Celsius also, and at the same mass flow rate of 1000. And Basaka's bowl comes out at 21.81 Celsius, losing more heat further. And then it goes into third heat exchanger. Mary's bowl, this time around, the third bowl Mary introduces to the heat exchanger, is at a temperature of 0 Celsius, but having a mass flow rate of 3000, which means this frozen bowl contains more soup than any of the 2 bowls she added to the heat exchanger previously. So it comes out at a temperature, this same third bowl comes out at a temperature of 5.73 Celsius, gaining a temperature of 5.73 Celsius from Basaka after the thermal energy transfer. And the mass flow rate is still intact because it doesn't change in heat exchanging. And Basaka's bowl finally comes out at a temperature of 5 Celsius. With that, Basaka has achieved cooling, and Mary's frozen soups have achieved heating. And this here is the concept of heat exchanging using a heat exchanger train. And it is nothing more than heat exchangers optimization. Instead of using 3 heaters and 3 coolers, you just use 3 heat exchangers to do heating and cooling simultaneously. Saves time, cost, utility, resources. Very convenient, a very beautiful thing in process engineering operations. So, with this, we come to the end of this week's content. And as always, if you followed us down this far, please make sure to subscribe, like, click on the notification icon, and drop a comment if possible, as all these goodwill would allow us to be able to create more content through your motivation. Thank you very much.